Observe the surface of this pond. The lily pads grow in varying sizes, drifting and coming to rest against one another. Look closer to see a strict physical negotiation. Round edges touch, boundaries align, and gaps of dark water remain between the leaves. These plants navigate a complex spatial puzzle as they grow. Each pad finds its place by following the rigid constraints of geometry. This is circle packing, the geometric challenge of fitting round objects into a confined area as efficiently as possible, without any of them overlapping. This packing geometry dictates the internal architecture of diverse systems. It determines how atoms cluster into stable molecules and how engineers organize materials. To organize round shapes, humans rely on grids, aligning identical circles in rigid rows and columns. However, this leaves large four-pointed gaps where circles meet. Because of these voids, this arrangement covers about 78.5% of the available surface. The rest is empty. We pack them tighter by staggering rows. Each circle slides into the dip created beneath it, creating a hexagonal pattern. This shift creates a new rule. Any single circle perfectly touches edge to edge with exactly 6 surrounding neighbors. Closing those gaps increases coverage to 91%. For identical circles on a flat surface, this staggered pattern is the limit of efficiency. Industrial designers use it to bundle glass strands inside fiber optic cables, fitting the maximum number of fibers into the smallest possible space. Even at 91%, some space remains. To eliminate that last 9% of empty water, we must move past circles of identical size. This is Apollonian circle packing. When 3 circles touch, they create a curved triangular gap in the center that perfectly fits a specific smaller 4th circle. Adding that 4th circle creates 3 new, even smaller gaps. You can calculate the exact radius needed to nest a new circle into every one of them. Repeating this rule turns the geometry into a fractal. Every layer of circles shrinks to fit the newly created voids. By the 5th iteration, the complexity grows to include hundreds of tiny circles, each packing into the shrinking slivers of space. This process stretches infinitely downward, perpetually dividing the empty space into smaller and smaller segments. This particular model represents the absolute mathematical extreme of how tightly physical boundaries can be pushed without intersecting. This geometry can be mapped as a graph. By connecting the centers of touching circles, a network emerges. In physical structures, pressure and force travel where these surfaces meet, turning a collection of circles into a stable, load-bearing network. Look at the lily pond again, focusing on how the leaves share the water. The lilies utilize the same logic as the Apollonian fractal. By growing smaller leaves to fill the gaps between the larger ones, the plants maximize the surface area exposed to sunlight. Mathematics provides the formal vocabulary to describe this optimization. It allows us to calculate and recreate the same efficiency that these plants achieve through survival.